So to get started, what is the difference between the Taylor polynomial of a function, and let's just take an example. Let's take f of x equals sine x, maybe, as our first example for today. What is the difference between a Taylor polynomial for sine of x and a Maclaurin polynomial for sine of x? So let's contrast before we compare. What's the difference between these two ideas? A Maclaurin polynomial is centered at 0. Right. Centered at what we're going to call a equals 0 or x equals 0 or something like that. Where is a Taylor polynomial centered? Wherever we want it to be. Right. So in that case, we can think of a Maclaurin polynomial as just a special case of a Taylor polynomial. In other words, we're going to build both a Taylor and a Maclaurin polynomial in exactly the same way. It's just that in a Maclaurin polynomial, we're going to choose 0 to be our center point, whereas if we don't choose 0 to be our center point, we're going to call it a Taylor polynomial instead. So that's the only real difference in terminology, is that for whatever reason, Maclaurin had his name attached to the center point at 0 case, and Taylor had his name attached to the general case. But the good news is, what's the same about these two? How are they the same, Jessica?
They produce the same graph?
They produce the same, well, okay. I would say that they're constructed in the same way. As one another. So just getting the terminology up front. Saying Maclaurin implies that our polynomial is centered at x equals 0. Saying Taylor means that it might not be. It might be centered somewhere else. But with all of that in mind, let's just take by way of example f of x equals sine x. And let's build a Maclaurin polynomial which approximates f of x equals sine x. So how do we do it? What do we really need to do if, for example, so we'll start the whole process by taking sine of x, and we're thinking of sine of x as being kind of a complicated function, right? It's actually quite challenging to describe to a calculator or to describe to somebody who only knows how to do arithmetic what the sine of an angle means. It's a nasty function. It's a transcendental function. We can't compute the sine of something just by adding, subtracting, multiplying, and dividing. But we can come pretty close. And to come pretty close, what we're going to do is just single out a point. In this case, we're going to single out x equals 0. And we're going to measure the value of sine of x at x equals 0. What is the value of sine of x at x equals 0? 0. The sine of 0. And so if I'm going to build a Maclaurin polynomial that approximates f of x equals sine x, the first thing that I should require is that my Maclaurin polynomial also takes the same value at x equals 0. In other words, if I call my Maclaurin polynomial p of x, then at x equals 0, p of x should also equal 0. And if I do that, really what I'm requiring is that my polynomial pass through the origin, pass through the point 0, 0. So if I just quickly keep track of what p of x might look like, down here on the bottom, if my goal is to start building a polynomial that satisfies these certain requirements, then what does a polynomial look like? A polynomial looks like a constant, perhaps, let's call it a, plus another constant times x, plus another constant times x squared, plus another constant times x cubed, and so on, right? Let's say we just go up to x cubed for the moment. So this is in general what a polynomial looks like, right? It's a sum of a bunch of powers of x, maybe with some coefficients out in front of them. Well, what happens to this polynomial when I put 0 in for x? Yeah, exactly. If I put a 0 in here for x, then every term which has x as one of its factors is going to disappear. So p of 0 is going to just be a. Which means, up in my table up here, up in the chart that I'm starting to construct, if I want p of 0 to equal 0, what does that tell me about my Maclaurin polynomial? Well, it tells me that I want the value of a to be 0. Right? So let me rewind for a second and explain that one more time. So we have this polynomial, a plus bx plus cx squared plus dx cubed. And so far, what we know about this polynomial is we want, when x is equal to 0, we want this polynomial's value to equal 0. But when I plug in 0 for x, all the x's go away. And I'm left with just plain a. So if I want my polynomial's value to be 0, then I need a to be 0. That make sense? So what we're doing, the goal of this whole process that we're about to undertake here, is we're going to figure out what the values of those constant coefficients a, b, c, d, and so on should be in order that this polynomial match the sign of x as closely as possible. And the very first requirement is that just like sign of x, when I plug x equals 0 into this polynomial, I should get the value 0. But that requirement leads to the conclusion that a must equal 0. In other words, now we know something about our polynomial that we didn't know before. It doesn't have a constant term. Its constant term is equal to 0. But if I graph that function, p of x equals 0, then what does that function look like? If I graph it, it's just a horizontal line. So it doesn't really match the graph of sine of x very well, at least not yet. So if we want it to match more closely, what we can require is that not only does our polynomial match the value of our function at x equals 0, but it should also match the slope of our function at x equals 0. And how do I find the slope of the graph of f of x equals sine x? Take the derivative, right, exactly. We're looking for the slope of a tangent line to this graph. And in fact, so I'm going to take the derivative here. Derivatives. When I construct a polynomial whose value at x equals 0 and whose slope at x equals 0 both match sine of x, what I'm really constructing, as Williams says, is I'm really constructing a tangent line to our graph. In fact, that's exactly what a first-order Maclaurin polynomial, or in general a first-order Taylor polynomial for a function is. It's just the equation, it's a function whose graph is a tangent line to our curve. So to match that slope, I take the derivative of sine of x and I get cosine of x. And what is cosine of x's value at x equals 0? Cosine of 0 is 1. Very good. So now our requirement is that when I take the derivative of my polynomial, so when I take p prime of x, that p prime of 0 should be equal to 1. But now let's take the derivative of this polynomial. What's the derivative of bx? Just plain b. Remember, b here is a constant, so we don't need the product rule or anything nasty like that. So when I take the derivative, I'm just going to get b. What's the derivative of cx squared? 2cx. So don't forget that 2. That becomes kind of important here. And the derivative of dx cubed? 3dx squared. Very good. Again, that 3 becomes pretty important. Not immediately, but down the line. So there's the derivative of our p of x. And if what I want is that this derivative, when x is equal to 0, is equal to 1, then let's plug in a 0 for our x and see what happens. Well, what do I get in this polynomial if I plug in a 0 for my x? Yeah, all of my terms disappear except for that first one, namely b. So, if I want my polynomial to have a derivative equal to 1 at x equals 0, then I must conclude that the value of b must be equal to 1. So if we go take this new information that we just discovered that b is equal to 1, we now understand our original polynomial better. Our original polynomial, p of x, was equal to a plus bx plus cx squared plus dx cubed plus et cetera, et cetera. But we determined that a was equal to 0, and so that first term went away. And now we've determined that b is equal to 1. And so now we know a little bit more about our polynomial. And if we forget that the rest of this is here, if we just take this expression up to first order, which now, this is the answer to our original question. The original question is, find me a first order Maclaurin polynomial for f of x equals sine x. Here it is, p of x equals x. And the graph of that function is actually the graph that's shown here on the app, the graph of y equals x, which happens to be exactly a tangent line to f of x equals sine x, passing through the point x equals 0. So the first order Maclaurin polynomial, first order Taylor polynomial, those are the same things as the tangent lines to our function. Changing the center point of our series. So changing the center point, in other words, the point at which we're finding all of these derivatives and matching them, is just going to give us a different tangent line. And so here are the first order Maclaurin, not Maclaurin anymore, but Taylor. Here are the first order Taylor polynomials for f of x equals sine x, taken at a variety of different points. And so our particular example is taken at the point x equals 0, and the first order polynomial is p of x equals x, the equation for which you can see down at the bottom right. So now we've matched up these polynomials up to first order. Let's suppose that we wanted more. Suppose we wanted to go up to third order instead of first order. Now, in addition to matching the value of the function and matching the value of its first derivative, we also are going to have to figure out the next couple of coefficients along the line. We're going to have to go back to our unknown polynomial down here and figure out what were b and what were c, because those were things that we didn't yet know. So c times x squared plus d times x cubed. So let's figure out what c and d should be in order to get a third order Maclaurin polynomial. In other words, a cubic function that matches up f of x equals sine x as closely as possible near the point x equals 0. So now that I have the 0th and first order derivatives matched up, my next step is to try to match up the second derivatives. So what's the second derivative of sine of x? Negative sine of x. So when we said at the beginning of this discussion that we're taking a lot of derivatives, yeah, we're going to take a lot of derivatives because we want to match up a lot of derivatives. What is the value of minus sine of x at x equals 0? Yeah, minus the sine of 0 is 0. And so what we want to do then is match up the second derivative of our polynomial at x equals 0. So let's now to match up what's going on with our polynomial. Yeah, sir.
Why is it dx to the fourth?
Oh, sorry, it should be x to the third. You're right. That's my bad. There. Yep, x to the third, sorry. So now in order to match up the third derivatives, we need to find the third derivative of our polynomial and then match that up with the value -1 to figure out what d is. But again, retracing our steps. The first derivative of p of x, first derivative of p of x was 1 plus 3dx squared, which at x equals 0 was equal to 1. The second derivative, my 1 is going to go away, and 3dx squared becomes, as we said before, 6dx, right? But then the third derivative is going to be just 6d. And so now the requirement is that 6d is equal to negative 1. So what's d? Negative 1/6. That's interesting. Negative 1/6. So now retracing our steps. Now that we have the values for all of these coefficients, we can backtrack and write down our third order Maclaurin polynomial. P of x is equal to 0 plus 1 times x plus 0 times x squared plus negative 1/6 x cubed. And that would be our third order approximation. Again, we got it, longhand anyway, we got it by matching up the values of the 0th, 1st, 2nd, and 3rd order derivatives of sine of x at the point x equals 0 with the values of the 0th, 1st, 2nd, and 3rd order derivatives of our unknown polynomial at x equals 0. And by making those matches at x equals 0, we determined one by one what the coefficients of that polynomial should be. So when we increase the degree of the Maclaurin, in this example, polynomial that we expect, so here's the first order Maclaurin polynomial. If I go up to second order, remember our second order derivative was equal to 0, and so we actually didn't get an x squared term in our example. I'll try and scroll this down so we can see it. Here we go. So our second and our first order happen to be the same thing, because the coefficient was 0 of the x squared term, so we didn't get anything new. But when we went up to third order, sorry. Okay, here we go. So when we went up to third order, the graph of our polynomial approximation, and there it is down in the lower right, P of x equals x minus 1/6 x cubed, is no longer a tangent line, but you might call it a tangent cubic, right? It's a cubic function, and this cubic function matches up with sine of x near the point x equals 0, right there at the origin. It matches it up better than any other cubic function can. In particular, it matches it up better than any line can. So we're kind of just generalizing the idea of a tangent line to now admit the idea of a tangent parabola, or a tangent cubic, or a tangent quartic, or a tangent quintic. And every time we increase the order of our approximation, we're going to get a graph which probably, anyway, hugs the graph of f of x equals sine x better than the one before it. So let's see the extent to which that's the case. That if I increase the order, I end up getting besides going haywire here. So let's really all I wanted to do was increase the order, not change the center point. But as I increase the order, going from a cubic to a fifth order that now matches sine of x even better, to a seventh order that matches sine of x even better, that the higher order and approximation that I get, the better it approximates the graph of sine of x. And I can do this same process if instead of using x equals 0 as my approximation point, if I use different places as my approximating points, then I can get polynomials like, for example, this one at the point x equals pi over 2. Now this polynomial matches f of x equals sine of x better than any other eighth order polynomial does near that point where x is equal to pi over 2. So I sort of have two different things to choose when I ask for a Taylor or a Maclaurin polynomial. First of all, what point am I trying to approximate this complicated function at? That's what we call the center point. And then secondly, to what order would I like to match it up? And this example, for instance, shows an eighth order polynomial graph that matches f of x equals sine of x better than any other eighth order polynomial can near the point x equals pi over 2.